So in this talk, we saw the problem when an engineer is trying to build consciousness. You need to bring all the senses together, use a lot of energy, and try to hope somehow they will arise into something akin to emotion. But what if you just cannot do it? What if just computation in a classical world is not enough to become conscious? So our last speaker is, of course, Roger Penrose, who's been thinking about this for a very long time. And we are very lucky that he found some time to come and tell us about it. Thank you.
Well, thank you very much for giving me the opportunity to waffle on a subject which has interested me for a long time. I'm not going to talk about interesting things like octopuses and bats and things like that, which is fascinating, nor about emotions, which is clearly something to do with consciousness, but two boring old numbers, mainly, to begin with at least, natural numbers. What's a natural number? Well, that means 0, 1, 2, 3, 4, etc. When I say etc., you get the idea, but I'm not going to say any more about that. Okay, well, what I want to talk about really goes back to about 70 years ago. I could have given this talk perhaps 70 years ago, at least most of it, because it emerges from a course of lectures that I went to when I was a graduate student in Cambridge. And I went to 3 courses of lectures which were nothing whatsoever to do with my subject. I thought 3 years is a long time, and so I can spend my early years doing some other things which weren't connected with my topic, which was in pure mathematics. Of course, that was a stupid idea because I didn't finish in time anyway. But nevertheless, I went to a lecture by Hermann Bondi on general relativity. Had a big influence on me later on in life. Wonderful lectures, I should say. Also, I went to a course of lectures by the great Paul Dirac on quantum mechanics, which also had a great influence on me. But the third lecture course, which was nothing to do with what I was supposed to be doing, was a course by a man called Steen on mathematical logic. And it was really about numbers, 0, 1, 2, 3, 4, etc. And, well, you see, how do you... In mathematics, you want to say things, not that just 3 plus 2 equals 5 or something like that, or bigger numbers than that, or huge numbers like what computers can do. No, you want to say something about all numbers. Well, you learn in school, I hope you still do, I'm not quite sure what people learn in school nowadays, but the process of mathematical induction. So you can prove something is true for all numbers by just proving a couple of things. For mathematical induction, you want to show something's true for all n, all natural numbers n. Then you can say if it's true for n, then it's true for n plus 1. That's one thing you show. And then you show it's true for n equals 0. And that shows it's true for all numbers. So I was really fascinated by that idea. You just do a finite number of things, and you can show something is true for all numbers, all natural numbers, let's say. When I say natural number, I mean a non-negative whole number. Now, this course of lectures talked about this famous result due to Kurt Gödel, which I didn't really like the idea of because it seemed to show that there were things in mathematics you couldn't prove. I didn't like that idea at all. Anyway, so I went to the course. It was fascinating. And the first part of the course was really mainly about computability, the very notion of computability, which is very much part of what computers do, of course. Well, that's the name. And that was interesting. But then he did talk about this famous theorem of Gödel. And it wasn't really it was something quite different in a way, not that there were things you couldn't prove, but what was it? Now, suppose you have a certain set of things that you can use in a proof. See, a mathematical proof, you have a certain set of axioms, and then you have a certain set of rules of procedure. So you have these axioms, and then you can combine them together in various ways, And if you can get the result out that you're trying to show, such as, for example, well, a simple example would be if you add two even numbers, you get another even number. A not so simple example would be a number due to a proposition, a statement, a theorem due to Lagrange. Well, actually, an interesting theorem because the great Leonhard Euler tried to prove it and couldn't, so it's quite interesting. That is to say that every natural number is the sum of 4 square numbers. That's a good example. And it's telling you about all numbers. It's a finite statement and not so easy to prove, but nevertheless, you can prove it. Now, what does the proof mean? Well, usually it would mean you have your set of axioms and rules of procedure, and if you use them correctly and you derive this result from those axioms and rules of procedure, then you've got a proof. Now, what did Gödel do? It was very clever, and I won't go into the details of the cleverness. They're quite tricky in some ways. But what he showed was that you could make a statement which in effect said, I am not provable by those rules. And it's a definite mathematical statement. You can construct it, and in the interpretation, you see what it means and how it's constructed, and it says, oh yes, it does really mean that. If you understand what these things mean, it means I am not provable. When I say I am the statement talking, if you like, I am not provable by those rules you've given me. Okay, well, you can say, well, maybe it's false. Well, if it's false, then it is provable by the rules, and therefore it has to be true. It has to be true, but it's not provable by the rules. Well, this is very strange. You've got something which is true. You know it's true. How do you know it's true? Not by using those rules, because it's not provable by those rules. You know it's true because you understand why the rules only give you truths. And I think that's really very remarkable. It's your understanding of why the rules work gives you more than using the rules. What does that mean? What does understanding what the rules mean? Well, it's this awkward word, understanding. What is understanding? Well, it's something that involves consciousness. You see, it's a sort of, in the ordinary use of language, you say, an entity, does it understand something or not? Well, it rather implies, by the use of the word understanding, that it's at least aware of what it's trying to do. Can something understand something without even being aware of it? Well, not in ordinary usage. I mean, people might quibble about that. But the ordinary usage of the term understanding means at least it's aware of what it's thinking about or doing or something. Awareness, consciousness. So it does seem to imply that this is something to do with consciousness. And I found this very striking. As I say, about 70 years ago, I could have given that much of my talk, and I began to think, well, I'm a physicalist too, so I believe whatever's going on in our heads must be in accordance with the laws of physics. So there's whatever those laws are, they have to be something, well, could be something you could put on a computer. Well, then they would be computable, and then you would be back in the trouble with the Gödel thing, and it seems to me it's got to be something in the physical laws. As I say, I'm a physicalist. It's not something magic which comes in when whatever. That it is something to do with the organization of this stuff which is going in our heads or in the octopus's head or whatever. There's something going on there which is acting in accordance with the laws of physics, but is not really something computable. As I say, the beginning of the course I went to by Steen involved the notion of computability and all that stuff, and so I understood vaguely what that meant. More or less, it means what you could put on a computer. Now, this says that there is something beyond. The understanding of what you're doing seems to be something beyond what you could put on a computer. Now, of course, people might argue about that now. I think it's a strong case to show there are things which are not computable, which are going on in the physical world, and that includes this phenomenon of consciousness. But then I began to wonder, what in the physical world could possibly be non-computable? Well, I mean, put things on computers. Newtonian mechanics, sure, you can go ahead and do that. What about Maxwell's equations? You have a little bit of a problem with these things you have to worry a little about, which I think is a genuine worry, because these laws of physics depend on the continuum. They're not just about the natural numbers 0, 1, 2, 3, 4. They depend on filling in the gaps between the natural numbers, if you like. And that's not a trivial issue. I did take the view, which I still take the view, but that's not really the problem. You can put things well enough on a computer, even if they're not exactly the continuum, you can approximate them. I think there is a possible lacuna in the argument there, which I have often wondered about. But let's take the route, which I'm taking here. It's not that. You can get closely enough to the continuum with your natural numbers to put your computer to work. And, well, at that time, computers weren't so good at doing general relativity. The general relativity, the Einstein's theory of gravity and space and time and all that stuff, that theory, you can put it on the computer and you're doing the approximations in a normal sort of way. And nowadays, you can do wonderful things with these computers. The LIGO detector, you can know that there are black holes colliding and producing gravitational waves, and the signals are very well calculated, and you know exactly what's going on. So this is very much a computational issue. That's not where it lies. So it's not to do directly with these theories of the continuum or something. What about quantum mechanics? Well, quantum mechanics, it's a little bit unclear there. How about the Schrödinger equation? Which I said I went to Dirac's lectures and I learned about how these equations work. Simply differential equations. They can be difficult to use because there are many variables and so on. It can be quite tricky to use. But still, it's still computation in the same sense. Except that what is quantum mechanics? Well, it consists of two parts. People don't try to emphasize this very much. Einstein and Schrödinger certainly did. They said that, or even Dirac, as I learned later, said that quantum mechanics is not complete in some sense. I'm going to be a bit ruder than that. It's not just not complete, it's not quite right. Why do I say it's not quite right? Well, you see, what is quantum mechanics? What is the subject? Well, you have a thing called the wave function, the state vector, if you like, and the Schrödinger equation tells you how that state vector or wave function evolves in time. If you know what it is now, you will know what it is in 10 minutes, you'll know what it is in 100 years. So, according to the Schrödinger equation, it's a deterministic equation. You could put it on a computer to any precision you like. But the world doesn't satisfy the Schrödinger equation. I'm saying that quite brutally when I say quantum mechanics isn't quite right. This is what I mean. Why is that? Well, because the theory of quantum mechanics depends on something else than the Schrödinger equation. It's a thing which is rather impolitely called the collapse of the wave function. Schrödinger tells you how the wave function evolves, but the world doesn't quite do that. Every now and again, it does something else. What do I mean by every now and again? Well, Schrödinger made the sort of emphasis by this and by talking about his famous cat. People often misinterpret that, in my view. They say, well, it really shows if you had a really subtle system which you could actually have your cat in it and you could calculate exactly what happened according to the Schrödinger equation, then you could make a cat which is dead and alive at the same time. That's not what Schrödinger was saying. He was saying this is an absurdity. There's something wrong. And I believe he was right to say there is something wrong. There's something wrong. You see, what is the collapse of the wave function? Well, people usually interpret it and say, well, you look at the wave function or something, you measure it, you do a measurement on it, and this means you adopt a different procedure. You don't follow the Schrödinger equation, you follow another procedure which gives you a sequence of probabilities, and it's the probability of this or this or this or this, and that's what you do at that stage. You do something else in the Schrödinger equation. You collapse the wave function. You make a measurement. Okay, well, there are theories which tell you how that if the system gets involved in the environment, it gets so complicated, you use a different procedure. I won't go into all that. There's famous theorem due to Landau and von Neumann, which tells you if you take the environment into consideration, then you follow a certain procedure and you get this sequence of probabilities. If you look at it carefully, you see it actually involves what I call a double cheat. Or I say a cheat which is an ontology switch. That is, you have a certain view about how the theory relates to the real world, and then you change your view to something different. Technically, it's you change from the wave function to what's called a density matrix, and then you change it back again to probability mixture of different wave functions. And that's where you're cheating. You do a double cheat. It's a very good cheat, I would say. It's the sort of thing which gives you the right answer, and it's a really very impressive thing to do. I'm not saying that what Landau and von Neumann did was rubbish. Absolutely not. It was very clever, but it does involve this double ontology shift. Two cheats, if you like. That to do a big good physicist, you know how to cheat properly. I think that's part of the idea. And, okay, that's fine. Part of the game. But it's more important to see what's going on, what's really going on there. Now, I took the view, because of this first part of my talk, that what's going on has to be something which is not computable. Now, that's what's not a normal view about these things. People often would say about me, well, I waffle about consciousness, and all I'm really talking about is this teensy-weensy little thing which has to do with mathematics in a particular area or something like that. And what's that got to do with the main problems like, well, feelings and goodness knows, and what do I have to say about the different impression that blue and pink have? Sure, they look completely different, they feel completely different. I don't have anything whatsoever to say about that. I mean, of course, there are various things where certain conditions in the brain you get confused about, which is blue and pink and all that stuff. I don't happen to have that problem, but I have nothing to say. I had no idea. This little tiny weensy thing that I do have something to say about is this issue of computability, which tells me that there is something going on in consciousness, in understanding, in this very particular way in which consciousness is being employed, an important way, because it involves understanding, and in understanding of the world at some level or another is absolutely crucial. I'm sure it's true for the octopuses we just heard about. They understand something about what's going on, and that's very important to them. Now, what does understanding mean? Well, you have to be conscious of it. But I mean, that's going one way around, and it's not saying much about our feelings in blue and purple and whatever it is. But it is saying something about something. Which, the point I'm making is that it's telling it is that the consciousness thing that we're trying to search for seems to depend on something that goes beyond any of these theories I've talked about. But you see the clue, I claim, in quantum mechanics, because it's incomplete, or as I say in my ruder phase, not quite right. It's wrong in a certain sense, that when a system gets big enough that these superpositions being here at the same time, something like that, well, that was what Dirac was saying. I didn't quite gather the explanation he gave. I think I was staring out of the window and I missed it, which was probably a good thing, because that meant I never understood what he said, and probably what he said was something to smooth it over and stop you worrying about the problem. I'm sure it was something like that, and I didn't get that bit, so I did worry about the problem forever since, which is what on earth is going on, is something which is not in current physics. And it involves the collapse of the wave function, which is a physical process, and the laws of which are something we don't know, and which I'm claiming are not computational. That's, if you like, the only place that I could see it can seriously be in. There are other little possibilities it could be that not. I think this is easily the most likely. That it's in the collapse of the wave function that we have something beyond our present understanding which allows us to understand things or some way go beyond pure computability. And I guess people won't like this very much because modern computers, of course, they don't do the infinite things, you see. Well, at the beginning of my talk, I was saying, you can talk about the infinite, you can talk about it in a serious way, in a rigorous way, and it doesn't matter, your computer can, I think some of these very early results, I remember learning about Skew's theorem, which was something which was, those times it was some number which was absolutely huge, way beyond what any computer, even today, could get anywhere close to. And you had to get beyond this number to see that this result happened to be true. This happened to be a thing in number theory I won't bother you with. Anyway, so the point of view I had was this quality of understanding. It needn't be anything to do with mathematics. That's just where you see it. You see the role of being something beyond our physical understanding now. Now, all this is old hat. When I say I could have talked, maybe not 70 years ago, but maybe about 50 years ago, I could have given that talk. But there's certain ideas about this which are much more recent. I've tried to understand a bit more about the collapse of the wave function and how it relates to relativity. And it has a very curious relation to relativity. Let me give you a sort of example of this. I think in the early days, people used to worry about the wave function, and they said, is it real in some sense? Mathematicians who know what a wave function is said, no, it's complex. Oh, that's not what I mean. Is it really there? Or is it just some kind of artifact that we use in our calculations? And Einstein put forward a rather impressive condition. He said, something is real if you can make a measurement on it, and if this measurement gives you yes with certainty and without disturbing the system, then it gives you a reality. What I'm trying to say now is that it does give you a reality, but it's a kind of reality which is a little peculiar. It's what I'm calling quantum reality. And I make the point that there are different kinds of reality. There's classical reality, and there is quantum reality, and they're not quite the same. The main difference is that classical reality, you can ascertain it. I can take my sticks here and I say, hello stick, what's your shape? Well, it will say I'm more or less cylindrical up to here. I'm another slightly smaller cylinder, and I've got a little spike on the end and all that sort of stuff. And it can describe the shape exactly. Well, close enough. So that's what classical reality is like. You can say, hello state, and what is your state like? And it can just give you this description. Quantum reality is not like that. And I'll give you a good example. The spin of an electron, that's an example of a spin half particle. The spin of an electron, the state of that can be described by taking some direction, say the direction of my thumb, and it is spinning right-handed about that direction. Every state of spin is spinning right-handed about some direction. Now that is quantum reality. If I find a state and I want to say, hello state, which way are you spinning? It looks at me blankly and it says, I don't answer questions like that. Suggest a direction. So I might say, I know because I know the state came about from some complicated experiment. It would be spinning about that direction. And I can confirm by saying, are you by any chance spinning about right-handed about that direction? And the spin then says, yep, you got it right. Every time you got it right. And that is quantum reality. But if I say, tell me which direction you're spinning in, it says, nope, I don't answer that kind of question. That's the difference. So it's true about Einstein's idea of reality, but it's quantum reality. And this kind of reality is important to understand because it behaves very peculiarly with regard to time. And I did study this, and I wrote an article about this once. And the thing is that the fact that you can't ascertain it is important. You can confirm it, but not ascertain it. And there are experiments, there are things that are called EPR experiments, Einstein-Podolsky-Rosen experiments, and things like this, which seem to be very curious. They seem to indicate that signal can be sent from, well, it's always Alice and Bob are the two. Alice has a spin half particle, Bob has another one. They start from a stage of spin zero, and then they sort of spin oppositely to each other. And Alice makes a measurement. Instantaneously, Bob's state is going the other way. It's worse than that. It's before, backwards in time, his thing goes the other way. Does that contradict relativity? No, because it's quantum reality. Bob can't ask his state which way you're spinning. He can say, do you happen to be spinning this way? And then give you an answer. It's important to know that distinction, because quantum reality behaves very peculiarly with regard to time. It doesn't quite go backwards in time, but it does something rather like that. And I think it's important perhaps to relate this to things. When I wrote my book, The Emperor's New Mind, this was my first toying with these ideas and sort of writing a semi-popular book. And I thought it might inspire young people. I only got commentaries from old retired people who were old enough to spend enough time to read my book. But then I did get a message. Well, I have got some people from young people later, that's good, from Stuart Hameroff, who did read my book. And he got back to me and said, you evidently don't, he was a bit more polite than that, evidently you never heard of microtubules, have you? You see, I'd learned about the Hodgkin-Huxley theory of nerve propagation, and I realized that's hopeless. If you wanted to preserve quantum states, it doesn't do it. I mean, it disturbs the environment too much, and that's not what you want. If consciousness couldn't be just by nerve propagation, there had to be something else. And he said, well, how about microtubules? Well, I won't go into that story, and I think it's an important story. Seems to me there is a reasonable chance that there is something in the microtubules which requires quantum reality notions, and there could be something more. In fact, there are certain ideas which Stuart has gone into. I don't really follow all these things now, but there's a certain layer of the brain. You see, one thing that I learned sort of elementary things about neurophysiology, and one thing, they were sort of blatantly obvious things. One is the things that the cerebrum and the cerebellum are different. The cerebrum has this stupid crossing over. Some people say, oh, it's a mistake or something. No, it's not a mistake. The other is this cerebellum, which didn't make that mistake, no. Cerebellum is right-hand side goes the right way, and the left-hand side controls and is controlled by the left-hand side. There's none of this stupid crossing over. The cerebrum does all this crazy stuff. It's doing it for a reason. I don't know what the reason is, but there is obviously something else going on than just nerve propagation. And I think he's right in that. And I didn't know that anything which is different between these two parts of the brain. And then he points out, well, there's certain cells called pyramidal cells where the microtubules have all different organizations and things like that. I didn't want to go into that. I don't understand it myself. But the claim is that you could maybe, you see, the issue which I was worried about, another issue, is it seems to be that things happen. I think in my book, The Emperor's New Mind, I did refer to these experiments due to Benjamin Libet, which seemed to indicate something very curious about temporal, when you actually experience something. When does a conscious feeling of something or other happen? And it seems the time is all messed up in some peculiar way. That it's not, somehow it goes almost as though it's retroactive. And maybe it is in some sense, because the quantum reality can do that. Classical reality can't. You've got to be damn careful that you don't get causality problems. But if it's quantum reality, it's not going to cause you a problem. I don't want to talk about this in any detail because, first of all, I don't understand it in any detail, and secondly, it would confuse everybody else. But I do want to say that there could well be something in what's going on in the brain which involves this quantum reality notion and these very curious experiments made by Benjamin Libet, which seem to indicate that there is something very puzzling about the timing of conscious experience. And it relates to the way, say you think of a ping pong player. I used to try and play ping pong in my youth. And it's clearly, you've got to want to make a decision. Am I going to flick the ball to the right or to the left? Well, I judged where my opponent is, and I think if I flip it this way, it's more likely it will be unexpected to my opponent. And that thought, sort of very rapid kind of thought, according to current views, is much too quick to be done consciously. It has to be unconscious. But I thought, no, I was thinking it consciously. But the view is that you could do this, maybe, if you realize that there's something about quantum reality involved in conscious experience. I'm only putting this out as a sort of slight feel of some kind. I don't have any theory of this, but I am indicating that it could be a much more subtle issue. Certainly than a computer, there's something much more subtle going on which could involve this difference in notion between quantum reality and classical reality, which is something there in the real world. It's in the real world, but it's very peculiar, certainly in relation to temporal orderings and things like that. Thank you very much.